Hi, my name is McMahon and I'm going to be doing my presentation on nuclear energy. First, we're going to be talking about what fission is, because in order to understand how a nuclear power plant works, you must know what fission is. And then we're going to be talking about a specific reactor, a breeder reactor, and the advantages and disadvantages to it. And then we're going to be talking about a disaster that occurred in Japan known as the Fukushima Daiichi disaster and how it released a bunch of radioactive materials into the atmosphere. So first, let's look at what fission is. So fission is the splitting of a large nucleus into smaller ones with the release of energy. This process can take place spontaneously, or it can be induced by the excitation of the nucleus with electromagnetic radiation in the form of gamma rays or many different particles, mainly the neutron. In this process, a large amount of energy is released because the products weigh less than the reactants. Radioactive products are formed and many neutrons are emitted. There are only certain elements that undergo fission under specific conditions. These factors include the size of the element, the number of protons and neutrons it contains, and the energy of the neutrons that interact with the nucleus to start the fission process. So now we're going to look at uranium, because uranium is what specifically undergoes fission in a lot of reactors. So if a uranium atom is neutral, it contains 92 protons and 92 electrons. In nature, uranium is found in two isotopes. 99.3% of uranium atoms contain 92 protons and 146 neutrons, making it uranium-238. 0.7% of uranium contains 143 neutrons and 92 protons, making it uranium-235. This is a less abundant isotope. These isotopes are unstable, meaning that they will undergo radioactive decay and change forms over time. Now we're going to look at the nuclear fission equation. Okay, so first, the nucleus of uranium-235 collides with the neutron, which creates a heavier isotope of uranium-236. So it just stays here momentarily. Uranium-236 then splits into two smaller atoms, barium-141 and krypton-92, releasing 3 more neutrons and energy. So here I'm going to show you a little picture of what actually occurs. So here you have a slow neutron. It's going to collide with uranium-235. When it collides, it releases, it forms into uranium-236 momentarily. And then what happens is that then splits. It splits into two products, barium-141 as well as krypton-92. It also releases a large amount of energy and some heat, and 3 neutrons are also produced. Okay, so having neutrons on both sides of the nuclear equation is important for fission to continue. So every neutron that is produced can in turn strike another uranium-235 nucleus, causing it to split, releasing more neutrons to keep the cycle going. This is called a chain reaction, which is used to describe a reaction in which one of the products becomes the reactant, making it possible for the reaction to become self-sustaining. So that is what a chain reaction is, and this is just a picture showing it. So here we have uranium-235. Okay, so a neutron comes and it collides with this, making it uranium-236. It then splits into two products, barium-141 and krypton-92. It also releases 3 neutrons and some energy, but these neutrons in turn are then able to collide with some other uranium-235s and produce the products again and produce more neutrons, and the cycle keeps going. So that's very important for nuclear reactors. Okay, so now we're going to talk about what are the components of nuclear reactors. So in a power station, one or more steam generators and the primary cooling system is in a steam vessel inside a dome-shaped containment building. The turbines, which are non-nuclear, run the electric generator, as well as the secondary cooling system. This non-nuclear portion is connected to something that removes excess heat from the coolants. Inside the reactor core is the uranium fuel, which is in the form of uranium oxide. This fuel is the heat and width of a dime and are known as pellets. These are then grouped into stainless steel clad bundles or rods made of 200 pellets. When a fission reaction begins in the reactor, it can sustain itself through a chain reaction. However, neutrons are needed to begin this process. To generate neutrons, both beryllium-9 and plutonium, which is a heavier substance, are used. When together, plutonium releases alpha particles, which then strike beryllium, releasing neutrons, carbon-12, and gamma rays. These neutrons then begin nuclear fission of uranium-235 in the reactor core. Metal rods are found among the fuel elements, sucking out excess neutrons. The rod position determines the rate of fission. The fuel bundles and control rods are lathered in a primary coolant. When this coolant interacts with them, it carries away heat. This solution also absorbs the heat generated by the nuclear reaction as well as moderates the rate of fission. It runs in a closed cycle, going from the reaction vessel to the steam generators and back again. The primary coolant then sends out the secondary coolant, which is the water in the steam generators that does not interact with the reactor. Blades of turbines that are attached to an electric generator turn due to the hot vapor producing electricity. The water vapor then cools and condenses back to a liquid and goes back to the steam generator. This continues the heat transfer cycle. In nuclear facilities, cooling is done in large cooling towers. Also, water from lakes, rivers, or oceans are used to cool the condenser, carried out by a tunnel. So here's a picture. This is a pellet, and then these are a whole bunch of pellets. So there's 200 of them in each rod. And that's located within the core where fission occurs because those are made up of uranium. This is just kind of explaining it a little bit better if you like visuals, but this is the control rods. So this is what we just saw. This is where fission occurs. So what happens is that fission produces a lot of heat. The heat runs here and eventually a whole bunch of reactions occur and steam is produced. Steam is what is actually turning the turbines, which then produces electricities for cities. And then you need a cooling system. So a lot of times there is a specific coolant that's actually within the reactor, but it also uses large bodies of water. So the water comes in, it also cools it, and then the cycle just keeps going because fission keeps occurring. So what is a breeder reactor? So this is a specific type of reactor. So a breeder reactor is a nuclear reactor that produces more fissile material than it consumes. These devices achieve this because their neutron economy is high enough to breed more fissile fuel than they use from fertile material, such as uranium-238 and thorium-232. There are two types of breeder reactors. There's a fast breeder reactor, which is the one that we're going to talk mainly about, and there's also a thermal reactor. So currently, China, Russia, India, and Japan have operational breeder reactors. So this is just an example of a reactor that is located. It's located in Japan, and it's right by some water, by a body of water. So why were breeder reactors created? So breeder reactors were created because uranium-238 makes up almost 99.3% of the total uranium deposits. However, it is non-fissile. But if they could use uranium-238, it would be able to power reactors for hundreds of years. So they started looking for the means of making its use possible, until finally they found an answer in the form of a breeder reactor. So now we're going to talk about how a breeder reactor actually works. So the fast neutron reactor has many of the same parts as the average nuclear reactor. However, the process is slightly different. First, the fast neutron reactor uses a liquid metal coolant, usually sodium, and it pumps it through a baffle to be heated by the reactor core. The core is surrounded in a blanket of tube that contains non-fissile uranium-238. Uranium-238 then captures a neutron and in return gets a larger element, uranium-239. Uranium-239 then undergoes beta decay and forms neptunium-239, as well as it gives off a beta particle, which is essentially an electron with an atomic number of a -1. So it's just opposite of what a proton is. Neptunium-239 also undergoes a beta decay, producing plutonium-239 and another beta particle. Plutonium-239 is highly toxic and it can be used to make nuclear weapons. Now plutonium-239 is bombarded by neutron and it undergoes fission. The products released are barium-145, strontium-93, 2 neutrons, heat, and energy. Once the liquid sodium is heated, it passes through a heat exchanger containing more liquid sodium. A heat exchanger is a cluster of thin-walled metal tubes. Liquid sodium from the heat exchanger then heats water in a steam generator. Steam then drives a turbine to generate electricity. A fast reactor needs no moderator to slow down the neutrons. For this reason, ordinary liquid water, being a moderator and neutron absorber, is an undesired primary coolant for fast reactors. Now the thermal breeder reactor, it actually uses thorium-232 as its basic fuel or fertile material. It converts this isotope into fissionable uranium-233, which creates a chain reaction. In the thermal breeder reactor, water is employed as a coolant to remove the heat produced by the continuous series of fission reactions. So here we're going to take a quick look here. This is already what I just described, but just for a little visual, this is a fast breeder reactor. So first, liquid sodium is pumped through a baffle to be heated by the reactor core, which we can see here. It's pumped through this baffle. Heated sodium passes through a heat exchanger containing more liquid sodium. So here's your heat exchanger. Liquid sodium from the heat exchanger heats water in a steam generator. So here we go. And then the steam generator drives a turbine and it produces electricity. So that's just one of them. Now, what's so good about this? Well, we got waste reduction and recycling that is occurring at the same time. So nuclear waste became a concern in the 1990s. Breeder reactors started to get popular because they reduced actinide waste, particularly plutonium. The waste from a breeder reactor has a different decay behavior because it is made up of different materials. Breeder fuel cycles can recycle and consume all actinides, leaving only fission products. Fission products have a peculiar gap in their aggregate half-lives. No fission products have a half-life longer than 91 years and shorter than 200,000 years. After several hundred years in storage, the radioactive waste from a fast breeder reactor would drop to the low levels of the long-lived fission products. Now we're going to talk about some advantages and disadvantages of a breeder reactor. So a breeder reactor creates 30% more fuel than it consumes. After an initial introduction of enriched uranium, the reactor only needs infrequent addition of stable uranium, which is then converted into the fuel. It can generate much more energy than traditional coal power plants. Even 3 grams of uranium undergoing fission can release 10 times the energy produced by a ton of coal. Breeder reactors can use the uranium waste from uranium processing plants and spent fuel from traditional fission reactors, along with depleted uranium from nuclear weapons. Uranium-235 used by light water reactors is rare on Earth, and its reserves are likely to run out within 100 years. But on the other side, uranium-238, which is used by breeder reactors, is quite plentiful. So in the US alone, its reserves are expected to last about 1,000 years, which is very good compared to 100. So since it reuses fuel, the expenses for mining and processing of uranium ore are minimized, and this will also keep fuel prices pretty stable. So that's really good. But what are some disadvantages? So whenever there's good things, there comes with bad things. So breeder reactors use highly enriched fuels, which pose the danger of critical accidents. So they also work at a very high temperature and a fast pace. Plutonium persists for a long time in the environment with a half-life of 24,000 years, and it is highly toxic, causing lung cancer even if small amounts are inhaled. So to date, not a single breeder reactor has been economically feasible. Every year, billions of dollars worldwide are spent for the safe storage of plutonium produced, which is then useless as few reactors actually use it as fuel. It requires liquefied sodium or potassium metal as a coolant, as water would slow down the neutrons. These metals can cause a mishap as they react violently when exposed to water or air. These reactors are complex to operate. Even minor malfunctions can cause prolonged shutdowns. Their repair is tedious and it is also expensive. Now, to kind of wrap this up, we're going to be talking about a bad disaster that actually occurred, and it's called the Fukushima Daiichi disaster. So, the Fukushima Daiichi nuclear disaster in Okuma, Japan was caused by the tsunami following the Tohoku earthquake on March 11th, 2011. Approximately 30,000 people were evacuated from their homes, with one confirmed radiation-related death. After the earthquake, reactors 1, 2, and 3 that were producing electricity automatically shut down their sustained fission reactions. This was done by inserting control rods in a safety procedure known as SCRAM. Because the reactors were unable to generate power to run the coolant pumps, diesel generators that were installed for emergencies kicked in. These are designed to keep the power electronics and coolant systems running in times of stress. These were working normally until the tsunami destroyed reactors 1 to 5. Reactor 6 remained intact, trying to cool the neighboring reactor 5. Water then flooded into where the emergency generators were located. The water-filled diesel generators then failed, resulting in no power to the coolant water pumps. These pumps were needed to keep the fuel rods from melting because the fuel rods were still producing heat from fission. When the secondary emergency pumps, which are backup electrical batteries, ran out, the water pumps stopped and the reactors began overheating. Eventually, several hydrogen chemical explosions occurred. This insufficient cooling led to the melting of reactors 1 to 3, and radioactive material was released into the atmosphere. In 2012, a report went out stating that a disaster was foreseeable, and the concern had already been raised to the company. The report also explained that the company knew that the Fukushima Daiichi plant would never be able to withstand the earthquake and tsunami, but they kept running even though they knew that. Later, it was admitted that the company did not take stronger measures for the disasters from occurring. So that's very, very bad. And then lastly here, there were actually quite a few radioactive materials that were exposed into our atmosphere. So the radioactive isotopes that were released in large amounts were iodine-131, cesium-137, and cesium-134. So iodine-131 decays quickly and there are no longer detectable amounts in the environment. At the beginning of the disaster, it was a major concern. Large exposure of iodine 131 can lead to burns to the eyes and skin, and it can also affect the thyroid, leading to increased cancers. People can ingest it through food products or water, or if you consume products of an animal that has actually been contaminated with the isotope. Cesium-137 and 134 were released in greater abundance. During the disaster, levels in the ocean were 50 million times larger than before. However, these levels dropped dramatically after the first month. Fisheries off the coast of Japan were unaffected, although one closed for a cautionary measure as it was located close to the reactor. To this date, there have been no links between radiation and large die-offs of marine mammals, birds, or invertebrates. They have been attributed to other things such as viruses or warming water. Exposure to these radioactive materials can increase cancer risk due to the high energy gamma rays. When ingested, the toxic materials become distributed within the muscle tissue. The risk of these isotopes depends on many things, such as which material an individual is exposed to, how long a person is exposed to, and just some individual sensitivities. So the most significant long-term effects are to the people living closest to the plant, because when the radioactive material travels, the less harmful it becomes. So that is my presentation. Depending on whether people believe a nuclear reactor is a good idea or not, just depends on who you're talking to, because the idea of it is extremely great. It has a lot of potential. The only downside that's really big is that if anything ever occurs, like a leak within it, it can cause some serious damage and can kill many people very fast. So yeah, anyways, I hope you enjoyed my presentation, and thank you very much for listening. Have a good night.